Welcome to today's deep dive. I want to start by having you, the listener, just imagine a scenario for a second. Let's say we drop you into a brand new, completely unfamiliar video game.
Okay.
You haven't seen the controls, you don't know the physics of the world. What do you actually do?
You probably just mash buttons.
Right,
Yeah.
exactly. You poke around, you test the boundaries, you probably let your character die a few times just to figure out, what the enemies even do.
Yeah, you learn by failing.
Exactly. But pretty quickly, you figure out the underlying strategy. You actively learn from that friction. Now, think about dropping an artificial intelligence agent, even like a state-of-the-art language model, into that exact same multi-turn environment.
It's a totally different story.
It really is. Historically, the agent just doesn't do that. It will confidently run into the exact same wall, repeat the exact same sequence of flawed actions, or it just loops until it times out.
Right, it fails to adapt because it basically fails to explore.
Exactly. And that brings us to the mission for today's deep dive. We are unpacking this fascinating new research paper. It's titled Meta-al Induces Exploration in Language Agents.
It's a great paper.
Yeah, it's from a team of researchers at EPFL, ETH Zurich, and the EDAP Research Institute. And their whole goal, the core objective here, is figuring out how we can teach these AI agents to explore, learn from trial and error, and adapt to unseen environments.
Just like humans do.
Right, mimicking that human ability to kind of scout out a problem before actually solving it.
And, to really understand why this is such a big deal, we should probably establish the baseline problem space first. Like, why does standard reinforcement learning, or RL, fall short here?
Yeah, let's set the stage, because LLMs are already really good at certain things, right?
Absolutely.
Okay.
Large language models are great at answering single-turn questions. If you need a script written or some code debugged in one shot, they're exceptionally capable. But when you place them into these multi-turn environments, say a digital workspace or a game where they have to plan 10 steps ahead, standard training paradigms start to break down.
Because every action they take alters the board state.
Precisely. And in those environments, standard RL suffers heavily from what we call sparse rewards.
Sparse rewards.
Right. The agent wanders around randomly, maybe accidentally accomplishes the task, and then the RL algorithm updates the model's weights to aggressively reinforce that exact specific sequence of actions.
It just optimizes for stumbling across the finish line.
Exactly. The result is premature convergence. The model learns this incredibly rigid, often highly suboptimal strategy, and standard RL essentially locks it in. It lacks any incentive for active exploration.
Okay, let's unpack this. Because the researchers didn't just point out this flaw, they actually built a whole framework to bypass it.
Yes, they did.
They call it LIMR. That stands for LLM Agent with Meta-RL. And this framework is basically broken down into two main components. The first one really tackles that incentive structure you just mentioned. How do we make the AI actually want to explore?
Right, the why. And they do this through a concept called cross-episode training.
Which means what, exactly?
Well, think about a traditional setup. You usually judge or evaluate an AI on a single attempt, right? One episode. It tries the task, succeeds or fails, and you update its software based on that one isolated attempt.
Right, pass or fail.
But Lemur completely changes this by training the AI over a multi-episode trial.
A trial instead of an episode.
Exactly. Instead of one single shot, the agent is given, say, 3 consecutive attempts, 3 episodes to solve the task.
Okay, that makes sense logically, giving it a few tries. But how does the math actually reflect that? Like, if it fails episode 1, isn't the algorithm still going to penalize it?
That is the genius of it. That's where they introduce a specific trajectory discount factor. In the math of the paper, it's represented as gamma subtrash. And what this does is handle the credit assignment across the entire trial, not just the single episode.
Just looking at the big picture.
Exactly.
Yeah.
It effectively communicates to the agent that failing to achieve the goal in episode 1 is totally fine, mathematically speaking, as long as the agent gathers useful information.
Oh, wow.
Yeah, it heavily incentivizes the AI to spend its first attempt just exploring. The agent learns that poking around and mapping the environment in episode 1 gives it a much higher total reward if that information guarantees a quick, efficient win in episode 2 or 3.
I see. It's literally like sending a scout ahead to map out the terrain before sending in the main army.
That is a perfect analogy.
Because the scout isn't supposed to win the battle on day 1. Their job is purely informational. So Lemur is training the AI to be its own scout first.
Yes, it prioritizes information gain over immediate task completion.
Okay, here's where it gets really interesting, though. Because if we are running these multi-episode trials, How is the AI actually learning between attempt 1 and attempt 2?
Huh.
Because the paper is very clear that they are doing this without any traditional software updates. There are no gradient updates happening between these episodes.
Right. And running back propagation, tweaking the internal weights of a massive language model after every single failed click in a game is just computationally impossible. It would take way too much time and money.
Exactly. You can't run those updates on the fly.
Yeah.
So the researchers rely on what the model is already great at. They use a mechanism called in-context policy adaptation via reflection.
Okay, wait, so it's not altering its neural pathways at all? It's just using its context window.
Precisely.
Yeah.
It uses this concept of an inter-episode memory. Basically, after failing an episode, the AI is prompted to write a textual reflection.
Like a diary entry.
Exactly like a diary entry. It analyzes its own trajectory, identifies what went wrong, and drafts a strategic plan for the next attempt, all in plain text. A highly analytical diary entry. Can we ground this in a real example just to see how it works in practice?
Absolutely. Imagine we drop the AI into a text-based household simulation. Its assigned task is to heat an apple.
Okay, simple enough.
So in episode 1, it finds the apple, picks it up, walks to the microwave, and types the command, put apple in microwave.
And
The environment spits back an error. The action failed.
because the microwave door is closed, obviously.
Right. Now, a standard RL model might literally just keep typing, put apple in microwave, over and over, trying to shove the apple through a closed door until the timer runs out.
And then it just gets mathematically penalized for that whole run.
Exactly. But the Lammer agent stops. It reflects. It generates a text string that says something like, my previous sequence failed at the microwave. The environment returned an error. I realize I must first execute the open microwave command before inserting the object.
Oh, that's brilliant.
It goes on to write, in the next episode, my plan is, find apple, take apple, go to microwave, open microwave, put in apple, heat.
And then when episode 2 starts up, that exact diary entry is just fed back into its system prompt.
Yes. It reads its own strategic analysis from the previous failure and executes the corrected policy.
Bypassing the need for any actual software updates. It's just using natural language reasoning to course correct. That is so elegant.
It leverages the fact that LLMs are already world-class at text synthesis. It just turns that capability inward.
Okay, so they have the framework, they have the mathematical incentive to scout, and they have this textual reflection diary to learn from. But they had to prove this actually works, right?
Right, the proving grounds.
The researchers set up 4 really diverse test environments, and I want to walk through them because they push the AI in totally different ways.
The environment selection is critical here. It proves the model isn't just a one-trick pony.
Exactly. So the first one was Sokoban. That's that classic puzzle game where you push boxes around a grid onto targets.
It's fully observable, meaning the AI can see the whole board, but it's brutal.
Oh, yeah. One wrong push and the box is stuck in a corner forever. You have to plan so many steps ahead.
Then they move to partially observable environments, starting with Minesweeper.
We all know Minesweeper.
Right, a grid of hidden mines. You have to use logical deduction based on the numbers you reveal to clear the board.
Which means the AI has to manage uncertainty and calculate probabilities on the fly. You can't just memorize a path.
Exactly. For the third test, they completely shifted gears and used WebShop.
This one is so cool. It's a simulated e-commerce website.
Yeah, the AI gets a prompt like, buy me a red pair of running shoes under $50.
So it has to actually navigate search bars, parse through dense HTML text, click different product variations, and hit the buy button.
Completely different type of reasoning than a grid puzzle.
And finally, they used ALF World, which is that text-based household simulation we were just talking about with the apple and the microwave.
It's worth noting they used a base model called Quen34B for these tests.
Right.
But the researchers are very clear that the Lammer framework is model agnostic. You could apply this to other models.
Good point. So they deploy these Lammer agents into these 4 environments. What are they actually competing against? What's the baseline?
They tested against some really robust standard methods. They used prompting baselines like React, which prompts the model to interleave reasoning and actions in standard heavy-duty RL algorithms like PPO and GPO.
Proximal policy optimization, standard, highly optimized training methods.
Exactly.
So how did the Lammer cross-episode training actually stack up? Did the diary entries work?
They absolutely crushed the baseline.
Really?
Yes. They measured this using a metric called pass at 3, which is just the success rate given a trial of 3 episodes.
Okay.
Compared to the best-performing standard RL models, Lamer saw absolute performance gains of 11% on Sokoban, 14% on WebShop, and a massive 19% improvement on Minesweeper.
A 19% jump on Minesweeper just by letting it read its own reflections from the previous blown-up boards.
Right.
That is wild.
And what's fascinating here is the data they gathered on test time scaling.
Break that down for me.
It's the difference in behavior between standard RL and Lamer across those 3 attempts. If you look at the standard PPO models, their success rate is flat. From attempt 1 to attempt 3, it hardly improves at all.
Because they just try their rigid pre-learned strategy, fail, and then try the exact same rigid strategy again.
Precisely.
Ugh.
But the Lamer agents show this massive upward curve. Their success rates jump significantly between episode 1 and episode 3.
Meaning they are demonstrably gaining competence in real time. They are actively learning the specific layout of that exact Minesweeper board while they play.
It proves the framework works. It induces active exploration.
There's actually a really cool visual in the paper that backs this up. They tracked a metric called trajectory diversity.
It's the heat maps.
Right. They mapped out every single cell that AI clicked on in Minesweeper across different attempts, and it perfectly illustrates the difference in exploration.
Because if an agent always takes the exact same 5 steps, its trajectory diversity is very low.
Exactly. And the paper shows this perfect Goldilocks zone. If you drop a totally untrained model into Minesweeper, its diversity is huge. It clicks everywhere, almost randomly.
High diversity, but terrible success rate. It hits a mine instantly.
Right. On the other end, standard RL models like PPO learn one safe pattern. Maybe they only ever click the top left corner and they refuse to deviate, so they have very low diversity and moderate success.
They get stuck.
But Lamer hits that Goldilocks zone. The heat maps show it maintains a high diversity of actions, it explores the edges, tests different areas while achieving the highest overall success rate.
It actively explores different paths to find the best one, instead of just running a script.
Okay, so it dominates the standard tests. But the real test for any AI is generalization. What happens when you change the rules or make things harder?
Right, pushing it to its limits. To test this, they scaled up the difficulty. They added way more boxes to Sokoban, and they cranked up the mine density Minesweeper.
And the data shows Lamer still held its ground. Even at the highest difficulty, it kept a 5% to 10% performance gap over the standard RL models.
Its underlying logic didn't just collapse.
But the test that really blew my mind was the out-of-distribution test in ALF world.
Oh, the O test. That is incredibly telling. It highlights the difference between rote memorization and true strategy.
So get this. They trained the agents in that virtual house strictly on 4 types of chores: pick, look, clean, and heat. So the AI learns how to interact with sinks and microwaves.
Right.
Then, for the actual test, they threw totally unseen tasks at it. They asked the agents to cool an object, which means finding and using a refrigerator, and a complex task called Pick 2.
And this is exactly where standard RL falls apart. A model trained only to clean and heat has its weights optimized for sinks and microwaves. When you say cool, it has no idea how to map its old policy to this new objective.
Its performance drops off a cliff.
But the Lamer agent, it beat the standard RL baseline by a staggering 23% on that unseen cool task.
A 23% jump on a task it was never trained on.
It's a profound result. It proves the AI didn't just memorize the mechanical steps for heating an apple. It learned a generalized strategy for problem solving.
It learned how to explore a room, find new objects, read the error codes when a new action fails, and formulate a plan. It learned how to learn.
Yeah.
So what does this all mean for the actual mechanics of that learning? Because the researchers did an ablation study to figure out exactly what was driving these massive gains.
Right, an ablation study is where you systematically strip away parts of the system to see what breaks it.
And they focused specifically on that inter-episode memory, the diary entry.
They wanted to know what information is actually useful to pass from episode 1 to episode 2.
Which leads to a really surprising twist. Because initially, they gave the AI its full history, the raw trajectory. Every coordinate, every click, every error code from the previous attempt, plus the written reflection.
Which seems logical. You'd assume giving an AI all the raw, granular data would give it the best context.
But then they compared that to a setup where they deleted the raw trajectory entirely. They just gave the AI the reflection alone, just the short diary entry.
And the results were striking. The reflection-only memory performs significantly better across every single environment.
I mean, look at the Sokoban numbers.
Mm.
Feeding the AI the full raw trajectory gave it a 34.8% success rate. But when they restricted its memory to just the self-generated reflection, its success rate jumped all the way to 56.4%.
It's a huge leap.
Why does giving the AI less data make it perform that much better?
It comes down to how these language models process context. Think about a full trajectory log of a failed episode. It's basically 50 or 100 steps of pure noise. Move north, interact, error, move south.
Just a wall of text.
Right. Forcing the model to read hundreds of tokens of flawed execution data dilutes its focus. The reflection, however, distills all that noise. The AI processes the failure, abstracts the core mistake, and outputs a concise directive for the next round. Do not push boxes against the outer wall.
Oh, it's the difference between handing a manager a 50-page spreadsheet of failed sales calls versus just handing them a one-paragraph summary of why the pitch isn't working.
Exactly. The raw data is overwhelming and useless. The summary is actionable. A language model is a reasoning engine, not a raw log parser.
A concise, focused diary entry is just much better guidance than forcing it to reread its own clunky history.
And if we connect this to the bigger picture, this research from EPFL and ETH Zurich really highlights why you should care about where AI is heading. We are rapidly moving away from the era of the static chatbot.
Right. The days of just typing a prompt into a browser and waiting for a poem are ending.
We are moving toward AI as an autonomous agent, software that operates dynamically in unseen, multi-day digital environments.
But for those agents to actually be useful in the real world, they can't need a human to reprogram them every time a website changes its layout.
Exactly. The ability to autonomously balance exploration and exploitation without constant reprogramming is the holy grail. Lammer proves that embedding this learning loop into the model's context window works.
It's a huge step forward, and it actually leaves me with a final provocative thought that I want to pass on to you, the listener, to mull over.
Okay.
It builds entirely on that ablation study we just talked about, the reflection-only memory. In this paper, the researchers evaluated the agents over trials of 3 to 5 episodes. And we saw that the AI succeeds way more often when it abstracts its raw data into a concise text summary.
Right.
But what happens when we scale this up? Imagine we deploy one of these autonomous agents into a really open-ended environment and just let it run for thousands of episodes.
Just continuous operation.
Yeah. If the agent is constantly summarizing its experiences and then writing summaries of those previous summaries to manage its memory limit, what is the end result of all that abstraction?
That's a fascinating question.
Could this process of continuous textual self-reflection eventually lead to a generalized intuition that actually rivals human adaptability? A state where the AI doesn't even consciously calculate its next move because it has this foundational understanding built on a mountain of past reflections?
It's possible.
Or, conversely, without the raw data logs to ground it in reality, could the AI's reflections eventually drift? Could thousands of subjective diary entries eventually compound its biases, causing it to hallucinate an entirely skewed version of the world?
Drifting away from the objective truth of the environment.
Exactly. It is a wild frontier for autonomous systems, and this paper gives us a glimpse right into it.
It really does.
Well, thank you so much for joining us on this deep dive into the Lammer framework and the mechanics of active exploration. Keep questioning the research, and we'll catch you on the next deep dive.